Hi, how's it going? My name is Carl Diaz. I'm with the Learning Resources Center here at the University of Colorado, Denver. And today we're going to be just looking at some elevator problems, just looking at a few different things, just making sure you understand what's going on in terms of elevators and tension and stuff. So over here, we're going to be looking at how tension compares to the weight of the elevator versus over here, we're going to be kind of looking at the apparent weight of a person inside an elevator as it's moving, okay? So there are different things going on. So they're solved different ways, all right? So over here, we're just looking at the elevator itself and trying to look at what, how the tension measures up in terms of the weight of the elevator, right? Is the tension more, less, or equal? Now we know for either situation, if the thing's moving at constant velocity, which isn't speeding up or slowing down, all the forces are balanced. So we don't have that situation up here because why, right? I guess we could do it over here. Right, for the first one, right, if the elevator is moving at constant velocity, whether it's up or down, the tension in the mg will be there. There's no acceleration, right? So the sum of forces in the y are equal to 0, and tension minus mg, because there's no acceleration, are equal to 0. That's all we can do, right? At the most, we could say that, sorry about that. The most, we could say that tension is equal to mg. Right, and then for a second situation over here where we're looking at the person in the elevator, again, what I'm doing right here is just constant velocity. It's not what these situations are, and it's why I didn't do it, because we see that with constant velocity, right, that the net force is equal to 0. So you should be able to do these pretty simply, but we'll talk about those in a second. So this would, right, these are two totally different problems. This is looking how tension and the weight of the elevator compares. This is looking how the weight of the person in the elevator, how it's being affected as it moves, right? So either way, moving at constant velocity, there's no net force, so it's in equilibrium. So the tension will be equal to the weight here, but not when it's speeding up or slowing down, moving up or moving down, right? So we see here in this situation, we're moving up but slowing down. In this situation, we're moving up but speeding up. In this situation, we're moving down, slowing down. In this situation, we're moving down, speeding up, right? So when we draw a free body diagram, moving up, slowing down. So moving up means velocity up, right? But we're slowing down, so we know that acceleration has to be opposite of our instantaneous velocity. So that's pointing down. When we draw the forces on our object, tension's up, mg is down. This is mg, looks like ma, but it is mg. All right, and now we can write our free body diagram. We know in all these, the coordinate system's normal, positive y up, negative y down. It didn't draw, but we're assuming that. So acceleration becomes negative. So when we fill in this side of the equation, because we know Newton's second law applies because there's a rate of change in motion, we're slowing down. Newton's second law applies because we're speeding up, slowing down. Those are rates of change in motion. We know we're going to be applying Newton's second law to that, which is why we're starting with it, right? Now the sign of acceleration depends. Here it's negative, right? There's a negative sign there because acceleration is pointing down. When acceleration points up, it's not there. So that's what's going on these, all right? So there's our basic second law Newton equation, and we want to fill in this side from our free body diagram. So tension's up, which is positive, and mg's down, right? And then those are the only forces on the elevator, so that's equal to a negative ma. Again, it's negative because acceleration's down. Why is it down? Because it's slowing down even though the elevator is moving up. That's what that situation looks like. We got to make sure these free body diagrams are right. Okay, and then with all four of these, we're trying to see how tension compares to weight. So when we solve this equation for tension, we see that mg, right? mg is going to add over, but ma is negative, so mg is going to actually subtract from ma. So we can see when we're moving up but slowing down, the tension, right, is going to be less than the weight because the weight is being subtracted by some value, some ma, right? Ma is that value. It's subtracting, right? When it adds, that means the tension's more than the weight. Okay, but here, there's the weight, mg, and ma is subtracting from it. So the tension, right, it's going to be less than the weight. That's what that means because we're subtracting some value from mg, and that's giving us the value for tension. Now, moving up, speeding up. So now the velocity is moving up, and we're also speeding up, so acceleration's in that same direction, right? The rate of change of motion's in the same direction we're moving when we're speeding up. So we know that to be good, right? Then we want to draw the forces on our object, tension up, mg down. I mean, we can kind of get that probably out of the way, right? All of these, for a free body diagram, tension will go up, mg down, right? You can see for all those, right? It's this velocity and acceleration that's changing based off what we're talking about, right? So once we have all that, we want to draw, right? Again, we already know it's Newton's second law because we're speeding up, so rate of change in motion. So sum of forces in the y are equal to ma. Now acceleration's positive now, so it stays positive. Then we fill in this side of the equation from our free body diagram. So tension's positive, mg's down, so minus mg is equal to ma. And again, we're trying to see how tension compares here. So when we're moving up, speeding up, we solve this equation for tension. We see that mg is being added to ma. So we can see tension's larger than weight when we're speeding up, moving up, okay? All right, let's go to this next one. What if we're moving down, slowing down, right? So velocity would be pointing down because we're moving down, but we're slowing down, so acceleration is going to be the opposite way of we're moving. The rate of change will be opposite, right? When we draw our forces, we already said tension and mg, right? Tension up, mg down. And we want to draw a free body diagram, write our Newton law equation. So the sum of forces in the y is equal to ma. Again, we know there's a because it's slowing down acceleration, right? And it's positive, so the signs are good. Then we want to fill in this side from our free body diagram. So that's tension minus mg is equal to ma. There's no other forces on there. And again, we're just trying to see how tension compares to weight. So that's why we're solving this for tension. When we solve it for tension, we see that mg is added to ma. So tension is going to be more than weight because weight's being added to some value, right? So tension's more than weight. All right, now for this last one, we're moving down but speeding up. So that means our velocity's down, but we're speeding up. So acceleration needs to be in the same direction as velocity, right? Our free body diagram already said is tension up, right? The rope's pulling up on the elevator as the weight of the elevator pulls down on the rope, right? So they're opposite. I know it's Newton's second law, just making sure we keep acceleration negative. So we write sum of forces is equal to negative ma because acceleration is down. We want to fill in this side of the equation. So tension minus mg, right? Tension's up, mg's down, right? Is equal to negative ma because that's coming from over here, right there. Right? And again, then we solve this for tension, and we see when we bring mg over, mg is now subtracted from ma, just like we saw over here, right? So we see tension is less than weight, because there's some value subtracted from weight. So again, we can see when moving up, slowing down, or moving down, speeding up, tension is less than weight. When we're moving up, speeding up, or moving down, slowing down, tension is more than weight. That's what we can see from these and say, and whatever else you could want to do with those, right? You can use this basic equation. We could have solved it for the acceleration if we didn't know acceleration. Solve this equation for the acceleration, and you have that, right? Of the elevators that moves up and down if you need it. There's a lot of things you can do with that, but that's really what we focus on. Next thing we look at is we put people inside the elevator, and we kind of see like how your weight, right? You ever been in an elevator and you move up and your weight changes, you move down, your weight changes? That's what we call apparent weight, okay? So whether we're here or we're in circular motion, because you're going to hear this word again, okay? When we solve for apparent weight, we're solving for normal force. It doesn't matter what chapter we're in, okay? Whether it's this chapter or it's a different chapter, if we're solving for the normal force, if we're asking you to solve for apparent weight, we're asking you to solve for normal force of that system, okay? It's right up there. Super important. It's not just true for this chapter, for any chapter, okay? You got to remember that for circular motion. So we're looking at the apparent weight of the person, so we got to look at the person in the elevator, so we got to draw the free body diagram a little bit different. Tension isn't acting on the person, it's acting on the elevator. So the person doesn't get tension drawn on them, right? But the person is sitting in the elevator, they're putting weight on the floor of the elevator, and the floor of the elevator is pushing back on them, and that's what we call the normal force. So tension gets replaced, or normal force gets, tension replaces the normal force, not because of some mathy thing, but because of how we're looking at the picture, right? Now we're looking at the person's applying force to the ground, so the normal force is counteracting the weight. That's why they're balanced in the elevator. The rope is not attached to the person, so there's no tension attached to the person, so we don't look at it, all right? So same thing over here, but now we're just looking for apparent weight of the person as it's moving up, slowing down, moving down, speeding up, moving down, slowing down, okay? So we do the same thing, right? Moving up, speeding up, velocity, that means velocity's up, and acceleration, if we're speeding up, the rate of change in motion's up. So we want to start with that, right? We want to draw our free body diagram where normal force is up, mg's down, and again, every free body diagram will be like that, okay? I just explained why We're looking at the person's a person of interest, not the elevator, so we show the normal force in mg. Then we say sum of forces are equal to ma. We know it's ma because there's a change in motion. I'm not going to go through all that because it's everything that we said over here is the same for over here, what we said in terms of change in motion, acceleration, right? Then we want to fill in this side of the equation, but this time, again, it's normal force now is positive minus mg is equal to ma. And then we want to know the apparent weight of the person, what they're filling. So we solve for the normal force, right? The normal force is ma plus mg, so we can see that the weight is being added, right? So when they're moving up, speeding up, it feels like they're being, right, squashed into the ground because the normal force is going to match the force that you're applying into the ground, right? So the normal force is large. Here we're saying that it's larger than weight, right? There's some value added to weight. So the normal force is larger than weight, so you're going to squat. You're being pushed down into the ground. You feel like, right, you weigh more, essentially, right? Because it's your weight plus something. And again, n is your apparent weight. So if n is your apparent weight, that's how much you feel like you weigh. So you feel like you weigh more than you normally do when you're moving up, speeding up. What about when you're moving up, slowing down? Well, same situation, except acceleration's negative, right? You're moving up, velocity up, acceleration down, right? It's opposite of your motion when you're slowing down. So we're going to make sure that's right again. Free body diagram, normal force over mg. We want to write our second law, Newton's second law, it's describing this, but acceleration needs to be negative, right? That's why it's negative there. Then we fill in this side from our free body diagram. So normal force is positive, mg is negative, so minus mg is equal to negative ma. And then again, we're solving for apparent weight, so we solve for normal force, and we can see now mg is subtracted from ma. So that means that your normal force is less, so that means you're going to feel lighter as you're moving up but slowing down, and that's true, right? When the elevator starts to slow down, you go, oh, right? It feels like you almost can float in the air, and that's what this is saying, okay? Is that the normal force, right, is less than your weight, right? Your weight, and that's what's pushing back. It's less than your weight, right? So you're not pressing down on the floor as much as you would if you were just standing there, all right? Or in equilibrium is what we're saying. All right, so now moving down, speeding up, right? So we're moving down, velocity's down, and we're speeding up, so acceleration, velocity should match, right? Free body diagram is still the same, right? It doesn't change, it's normal force in mg. Then we want to write our Newton law, right? But acceleration's down, so we want to write sum of force in the y is equal to negative ma, right? And then fill in this side of the free body diagram, normal force minus mg. Mg is down is equal to negative ma, because a is down as well, right? And solving for normal force, we see again, mg is going to be subtracted from a, so when we're moving down but speeding up, right, we're going to feel lighter, which is also true. It feels like the elevator floor almost disappears from us and we float. That's how we get like gravity, right? We can feel like weightlessness, right? That's these two situations, but this is the big one, right? Where we really experience the weightlessness, and that's what we're trying to say. The mg is that you're subtracting from it, and if this object's, or is this more than this or equal, right? You're going to feel weightless. Okay, anyway, this last one here, moving down, slowing down. So now we're moving down, velocity's down, but acceleration's up because we're slowing down, so these should be opposite. So when we write sum of forces in the y is equal to ma, a will be positive, filling in this side from our free body diagram. Normal force is positive, mg is down, so minus mg is equal to ma. Again, solving this for normal force because they're just asking us for apparent weight. Normal force is apparent weight. This is telling us that ma is going to be added to mg, which means what? We're going to feel heavier when we're moving down but slowing down, which makes sense. When we slow down, we go, oh, when we do, we feel heavier. So again, this is helping you with tension in elevators, two different situations going on. I hope this helps. Please watch this again. Watch all the videos. Go to lecture, go to tutoring, go to SI. And I'll see you in the next video.